Okay, um, we are beginning lesson 11. This is Algebra 1, Module 1, lesson 11. We just finished up lesson 10, where we were determining whether numerical expressions, numerical equations were true or false. And we also looked at the difference between algebraic equations and numerical equations. And so lesson 11 deals with solution sets of equations and inequalities. So in this particular lesson, we're going to look at finding solutions to these equations and inequalities and how to write those solutions. And so we first start with, in your book, if you follow along, with the example that they give us, and they want us to consider this example right here, where we have x squared is equal to 3x plus 4, where x represents any real number. And as we talk here, when we talk about real numbers, we're really meaning decimals, fractions, integers, whole numbers, square roots, all those numbers that are in our real number system. Are the expressions x squared and 3x plus 4 algebraically equivalent? And the answer to that is just by just by looking at it, you can tell that the answer is this is no. Now that doesn't mean we can't plug a number in and have it satisfy the equation, but to answer this question, just by looking at it, the answer is no. Now, the following table shows how we might sift, if you will, through various values to assign to the variable symbol x in the hunt for values that would make that equation true. So you'll see that equation from the other side, and the equation, if you remember, was x squared was equal to, and then I believe it was 3x plus 4. So we're trying to find out what values make this side here equal to this side. And so they begin plugging these values in over here on this side. They just randomly pick 0, 5, 6, -7, 4, 9, 10, and they plug those numbers in, and they just basically do what we did in lesson 10. And they're trying to determine whether the statement is true or false. The numerical equation is true or false. And so as you see, they go down here, they find all these falses, and then all of a sudden, boom, they find where if they put 4 in, if they let x equal to 4, they find that that is true. And what you can see is 4 squared is equal to 12 plus 4, which is 16. 16 is equal to 16. So it turns out that one of the solutions to this equation is when x is equal to 4. Now, you've sort of heard me say that when you have an equation like this, that exponent will tend to tell you how many possible solutions are there. So there might be one more, and it turns out that there is one more. Take a moment and see if you can determine what that second solution is, because there's one more that makes this x squared equal to 3x plus 4, that makes it a true statement. I'll pause the video here for a second and see if you can come up with that solution. Okay, you paused the video and you've had a chance to think about it. Well, if you were to continue to plug in numbers, you might have plugged in the number of -1. So if I just plug in -1 and I just see what happens. -1 just happened to come across and said, well, this might work. And as it turns out, -1 squared is 1. And then 3 times the -1 is a -3 plus 4. And look, it turns out that makes it a true statement. And so the other solution is x is equal to 1. So your two solutions to this one are 4 and 1. Also in this particular lesson, you're going to be doing some of this where you're going to be possibly plugging in like we did in the previous example. And so here in example number 2 in your book, they're asking you to plug in 4 and this number that looks strange. It's 1 plus the square root of 2 and then 1 over pi and then 5. Now, how you would do that is just simply take 7 and then plus 4. And does that equal 12? Well, the obvious answer is no, that's false. And you keep going along here, and you just say, okay, 7 plus, what's p this time? P is 1 plus the square root of 2. Does that equal 12? And the answer is false. Nope, that doesn't equal. You decide. And the same thing here. If you go ahead and plug that in and use a calculator, you'll find that this is false. It turns out that the last one here, if you put in 5, yep, that does make it true. And in fact, that's the only solution. So 5 would be the only solution. P would be equal to 5. The solution set of any equation, as it reads here in your book, written with only one variable, is the set of all values one can assign to the variable that makes the equation true. And that's lesson 10 coming back to us. Any one of those values is said to be a solution to the equation. In example number 1, we had 4 and 1. Those solutions made a true statement. In example number 2, we only had one value, and that was 5. To solve an equation means to find the solution set to that equation. And that's what we begin to look at in this lesson. Now, in the next example, they give us this equation, and they want you to solve for the values of a that make a squared is equal to 25. Now, they give you the solution. One can describe the solution set in any number of ways. We're going to be describing it in words, in set notation, and also in a graphical representation on a number line. And so they show you what that looks like. In words, for instance, in this first example, a squared is equal to 25 has solutions 5 and negative 5. This would be how you would write it possibly in words. In set notation, you might see these little symbols here. You might see these little symbols here and some other notation that we'll get into in just a second. These symbols, that's what's called set notation. So you're going to hear us talk about set notation, and those symbols we're going to use. And then graphing, well, that's just a number line. That's just a number line. And you notice on this one, to graph the solution set, you'll notice that you have a dot here and a dot here in the number line for the two solutions of negative 5 and 5. Now, another case that we want us to look at is this one. Solve for a. Now, this particular one, is there any number times itself that's going to equal a negative 25? Think about that. Well, as it turns out, by the definition of multiplication of the same number, there is no number, so there's no solution. So in words, you would put, there's no solution. In set notation, you might put this little squiggly mark here and put this circle with a line through it. That's the empty set. There's no solution. And then graphically, so in words, no solution. In set notation, this little symbol here with a circle and a line through it. And as a graph, well, you would just draw a line and put some numbers on it. For instance, 1, 2, 3, and you would not put any circles in it, no dots. There's no solution. And so let's do one here to wrap up this lesson. We want to solve this one. We saw this one earlier, but we want to write it in words, set notation, and graphically. So to solve this, we're going to use our steps. So we would show our work by doing the opposite to P is what's happening. So it looks like we're adding 7, so we're going to subtract 7 on both sides. And that gives us P is equal to 5. So this is our solution. How do we write it in words, in set notation, and as a graph? Well, let's change the color, and this is how we would write it. In words, P, the solution to P, and we can even write the solution to P is all real numbers where P is equal to 5. In set notation, you can either put simple version, just put this with the little set notation symbols. You could also, and you might also begin to see this in set notation. The same signal, or symbols rather, P is real, and this symbol here that you're going to see quite a bit is real, spell real there, and this little line here that's thick. Now that's red, this is red, such that. That's in your book, such that P is equal to 5. And so you might see either one of these. This is obviously more simpler, and this is more detailed. And then finally, if you're going to have the graph, well, the graph is pretty simple for this one. You're going to put 5 in the middle. I'm going to put 6 here because we get larger as we go to the right, and put 4 here. And then because P is equal to 5, I'm just going to have a dot on 5. And that's it. Last one. What's different about this one is this inequality. We're going to solve this the same way we normally would. And we're going to actually subtract 2 on both sides. And we're going to have W is less or greater than 2. So here's our solution as an equation or inequality. This is an inequality. So any number that's greater than 2 is a part of the solution set. And so write it in words. So in words, the solution is all real numbers, hardly writing this, really can't imagine. All real numbers where W is, where W is greater than 2. So there's in words. In set notation, so you have W is real such that W is greater than 2. And with the graph, simply draw a line graph, put 2 in the middle, put your number in the middle, put a number on the right, which is going to be larger, and a number on the left. And then what you're going to do is just declare, since W is greater than 2, it's not equal to, so we're going to leave the circle open, and then shade to the right. Shade to the right. So all the solution values on this right here are solutions to this inequality. That will end up with our discussion of lesson 11. You should be able to take an equation or an inequality and write the solution in words, in set notation, and as a graph. That'll be it. We'll talk more in a little bit.